Homework 17, confidence intervals for population means, standard deviation known, video 3. All right, so let's talk about how to build this confidence interval. I guess we should first define what I mean by a confidence interval. A confidence interval is just an interval estimate that captures the population parameter at a certain confidence level. Keeping in mind that an interval estimate is just an interval centered at a point estimate, opened up a certain margin of error. Our goal is to open an interval that has a certain confidence level for capturing a population parameter. For example, if we're trying to estimate population mean, then we want to say that our interval contains the population mean at a certain confidence level. Now, what do I mean by confidence level? I think I'll explain that as I showed you how to actually construct a confidence interval. So let's take an example, kind of in the guise of our GPA example from previous videos. Suppose our sample mean is 2.75, and our sample size was 225, and we know that the population standard deviation is 1.5. Let's construct a 95% confidence interval for mu. Now, some of you are going to start really thinking critically about this type of problem and pose the following question. If we're going to try to estimate the population mean, which presumes that we don't know the population mean, how could you possibly assume that we know the population standard deviation? Because if you compare the formulas for the two, the formula for population standard deviation is very convoluted, but you would need the necessary information capable of calculating the population mean. So why does it make sense to not know the population mean but know the population standard deviation? The answer is you would be correct. And the next section in the book about how to do a confidence interval when you don't know the sigma answers that question. In short, you use the sample standard deviation, but you have to use a different distribution, but the protocol is exactly the same, aside from using a different distribution. All right, so before we construct this confidence interval, there are two assumptions or two criteria that must be satisfied. Criteria number one, make sure I'm consistent with the book. Criteria number one, the sample is a simple random sample. Simple meaning that everyone in the population could possibly have been in the sample. Random, basically meaning that everybody had the same chance of being selected. Sample. For our purposes, we will always assume our sample is a simple random sample, because if it's not, then the techniques for doing this are beyond the scope of this course. Criteria number two. The sample size is large enough, and large enough means greater than 30, or the population is normally distributed. Population is normally distributed. This sounds a lot like the criteria for a sampling distribution of X bar to be normally distributed. And in a moment, you'll see why it's the same criteria. All right, so we're going to build an interval centered at 2.75. The biggest obstacle right now is constructing the margin of error, so we know how wide to make that interval. Here are the steps for building a confidence interval. Number one, find or calculate X bar. Now, when I say find it meaning that it was given to you and located. I found it, it's right there. But sometimes you're given the raw data and you have to calculate the X bar. Now, if you have to calculate the X bar, then there may be some rounding issues because your last move is to divide by a number, which will usually invoke a lot of decimals. The rule for calculating X bar is to use one more decimal place use one more decimal place than the data uses. So for example, if all of our numbers were whole numbers and we were calculating their mean, we would round it to one decimal place. Or if all of our values had 2 decimal places and we calculate the mean, we would round it to 3 decimal places. So you just pick up 1 extra decimal place. Unless you're just given the X bar, in which case that's the number of decimal places that you use. All right, number 2. Calculate the critical value. Now, I haven't defined what a critical value is yet, but I'm about to. The critical value is tied closely to the confidence level. In this case, the confidence level is 95%. Now, what does the confidence level represent contextually in a confidence interval? Contextually, what the confidence level represents is the center area of a standard normal distribution. You remember the bell curve with the 0 in the middle and whose numbers represent z's. Again, the confidence level represents the center area of a standard normal distribution. So we would cut off 2 tails, equally sized tails, and the confidence level represents that center area. So we have 95% in the middle. The critical value, or actually I should say values, but we're only going to use one of them, are the z-scores that cut off the middle 95%, or whatever the confidence level is. Now, I'm going to introduce you to a new variable, but I don't want you to get too overwhelmed by it. When you see a confidence level, it is generically represented by 100 minus alpha %. So in other words, you think of the confidence level not in terms of what it is, but how far away from 100 it is. So for example, if we had a 95% confidence level, that would mean that alpha equals 5%. When we get to the videos about hypothesis testing, this will be called the significance level. But the alpha, lowercase Greek letter alpha, which looks like what some people call a Jesus fish, represents the unshaded area in a confidence interval. So in this case, our alpha would be 5%. Now, how are we going to use all this information to locate the critical value, locate the z's that cut off the middle 95%? Well, let's think about this one over here. And in the previous video, I showed you notation where z was subscripted with a number. The subscript represented the area to the right of z. So what percent of the area is over here to the right of this z? Well, if the middle is 95%, then the remaining 5% are these 2 tails. So if I cut the 5% in half, this is 2.5%. So alpha over 2 is 2.5%. So z of 0.025, 2.5% is a decimal, means the z that has 2.5% to the right of it. It's z-chart time. Remember that the z-chart tells you left areas, not right areas. So if we're going to look up this z-value, we can either look up the area to the left of it, or look up the area to the right and remember that the sign is incorrect. Let's go look up 0.025 in the z-chart. Now here's where you got to be careful, and this is where I wish I had a full-blown z-chart. We are doing the z-chart backwards. Normally what we do with the z-chart is we know the z-value and we look up an area and do something with it. If it's left area, we look it up. If it's right area, we look it up and subtract it from 1. If it's middle area, we look up both of them and subtract them. But if you know the area of a tail, 0.025, then you have to go inside the z-chart and find the area closest to it to locate its z. So you have to go on a scavenger hunt. Now, if you have a z-chart handy, and you should, go to the negative 1.9 row. Why that one? Because we're looking for 0.25. Excuse me, 0.0250. Remember, the areas have 4 decimal places, hence the extra 0. If you go in the negative 1.96 row, you will see this area, and it will be in the 0.06 column. So you find the area or the number closest to it, and then you go to the edges to locate the z. Now, this z can't be negative 1.96 because it can't be negative anything. It's to the right. So it's positive 1.96. That is the z that cuts off the right tail when the middle is 95%. So what's the z over here? Well, if we were to write it using the subscript notation, we would have to subscript it with the area to the right of it. But because of the symmetry of the distribution, we know it's just going to be the opposite of that z. So it's going to be negative 1.96. It's really not that difficult to locate the critical values. You just have to remember how the confidence level is used in constructing a confidence interval. The confidence level represents the center area of a standard normal distribution curve, a z-curve, if you will. If there's 95% in the middle, that means the remaining 5% make up the 2 tails. You cut that in half, you have 2.5% in one tail. Look up 2.5% or 0.0250 inside the z-chart. Inside the z-chart, go to the edges to find the z. And one of them is negative 1.96 and the other one is positive 1.96. It really doesn't matter which one you use because at the end we're going to do plus and minus. So as long as you use either, you're okay. I always use the positive one. Let me check the time real quick. I think this video has already run quite long. It has. So I'm going to pause this, and the next video will just be the continuation of this one. There are 3 more steps, but we've overcome the hardest part.